Okay, now let's go into the next problem. The next problem is also a little tricky. It's called count leaves. Okay, so the count leaves does something pretty intuitive. It counts the number of leaves in a tree. So in this example, we have 2 leaves because we have the tree of 2 and the tree of 3. And then here, we have basically, we have 1 leaf right here, we have another leaf right there, and we have another leaf right here, and we have another leaf right here. And that's 4 leaves. So how do we do this function? Well, again, let's think of in terms of the simplest possible case. So our base case is going to be is leaf on t. And if the initial tree we pass into the leaf, how many leaves do we have? We have 1. And then what we can do is realize that the number of leaves in any tree is just going to be the same as the number of leaves in the branches of that tree. If the original tree is not a leaf. So notice in this tree that this tree is not a leaf initially, but the number of leaves that we have is just the number of the number of leaves on every single branch. So that's the key idea here. So same with this tree. The number of leaves we have is the number of leaves on the branches of this tree, if the top layer is not a leaf. So that's the key idea here. So how do we find the number of leaves on the branches? Well, what we can do is notice that each branch is a tree. It's a simpler tree. So how do we count the number of leaves on a tree? We have a count leaves function. So what we can do is we can do count leaves on every subtree for the subtree in my t dot branches, and this will count all the leaves in the subtrees or the branches. So once I have that, all I need to do is each of these will give me a count of 1, so I just need to return the sum of that. So take the sum of all the leaves in, so this returns all the number of leaves entirely in my tree. So let's test this. And it works. So really make sure that you understand why this recursion works, because the key idea is to notice that the number of leaves in a tree, if it's not a leaf, is just the number of leaves in the branches of the tree. The sum of it. So because there are many branches, we have to count the leaves in each branch and then take that together, put that all together. And the way we put it together is by taking the sum. Alright, so now let's move on to our next problem. The next problem is map tree. Okay, and this is actually our last problem. So this map tree function is going to basically return a new tree that has every entry in the tree bound to the result of mapping a function f over that entry. So let's see an example of this. So here we have the function square, and what we do is if we map this on our tree, we get a new tree that has the elements changed to whatever it was mapped to. Same with this tree. So how do we do this? Well, again, let's think of a base case. So generally, it's going to be the case that the base case is whether we check if it's a leaf, but that's not always the case. So really think about it. But in this key, in this function, what's the simplest tree I can map something onto? Well, it's just a tree with 1 leaf. So if the tree is a leaf, then I'm just going to check, hey, I just need to return a tree with this leaf. This leaf has a value. I need to map that function onto that value and then return a tree that has the value. So return, so this is just a matter of doing return tree on the function mapped to the t dot entry. So this is a very simple tree. Then, if this is not the case, what I have to realize is I have to basically map my tree onto my root, and then I also have to find a way to map it onto every single branch. But notice that every single branch, as I've been saying over and over again, every single branch is a tree. So what do we have? Do we have a function that maps things onto trees? Well, that's our map tree function. So this is the way you should really think about these type of problems. Use the function itself to solve the problem for you. So this is kind of crazy, but this is why recursion is so cool. So what we can do is we just have to do return f. So we have to map the function onto the entry, and then go through every branch. So remember, the branches is represented as a list, and map our function on every subtree for the subtree in my t dot branches. And so once I have this, I have my definition of map tree. So let's test it, and it works. So notice how it seems like working with trees requires a lot of code and a lot of special cases. You have to go down this branch, you have to go down this branch, and there are going to be some problems that are going to be much harder than these, but a lot of them actually turn out to be very elegant and simple because we can use recursion so well. And again, this is another example of why recursion is so cool. They make these problems that seem pretty challenging very simple by just using recursion. So anyway, that's an example of some problems you can do with trees. Alright, now I want to finish this lecture off by talking about applications of trees. So of course, I'm not going to teach you something that's not useful. Turns out that trees are really, really useful in the real world. So one example is that they actually represent the file system in every computer. For example, in the Linux system, there's a root directory, then there's something for the user, there's something for the home, and each of these have subdirectories, and turns out that every subdirectory is just a branch in the file system tree. So that when they display, whenever you click on a directory, and ask it to display the contents, so it's really just displaying every single branch of that tree. And some of those elements in that branch could also be trees. So that's the key idea of why a tree is good for this, because every single subdirectory is also a directory, and a directory is represented by a tree. So that's something really cool. Now, another really interesting application of trees is actually with Google Translate. And this might seem really interesting to you because it seems like translation is the farthest away from a tree data structure you can think of. But turns out that the way sentences are structured, there's particular choices on how you can translate them into a different language, because every different language has a structure. But turns out that the best way to represent this is using something called syntax trees. And syntax trees are a very important topic in something called an area of research in AI and machine learning called natural language processing. And natural language processing uses tree data structures all the time because they have to split these problems into smaller and smaller subproblems, and they turn out to have this very tree-like structure. So anyway, just an interesting idea that if you're more interested in that, I encourage you to read about it. But there is some very complicated math and amazing ideas there. So, but anyway, exciting stuff. Now, on the topic of artificial intelligence, recently in the news you might have heard of Google's AI winning the game Go against the world champion of Go. So this is really, really amazing because the Go is such a complicated game, and it wasn't expected that an AI could actually beat a professional player because it relies a lot on intuition too. So how did the computer do this? Well, it turns out that we could actually represent the way we can it turns out that it's a really something called a decision tree. And decision trees are very, very important in AI because what the Google AI is doing is, hey, when I'm in a particular position, which of these moves is going to give me the most likely outcome of winning? So what it does is then it analyzes each of these decisions and figures out, goes all the way to the end using its amazing computing power and figures out, hey, what's the probability of this winning? And then whichever one has the highest probability, it'll usually pick that one up. But the actual way this is implemented is using a lot of machine learning and training it with examples and showing which ones actually win versus which do not. And this is a huge topic in machine learning. I definitely encourage you to look at exactly how this works, but it's really cool, but it also has a lot to do with trees. So this is one example where trees can be very useful. Okay, and then another example where trees are useful is something I've actually had experience with, Google Maps. So Google Maps, so it might seem a little weird how this can be a tree, but here I have an example of Google Maps just opening. So it displays some map, but one thing you can do with Google Maps is you can zoom in, and it shows you a closer up version of something you zoomed into. So let's say I zoom in some more, and zoom in some more. So how does Google do this? How does it know how to zoom into a particular location? Well, turns out that by zooming in, it's really picking out the images from the next level inside a tree. And you might be wondering, how can a tree represent something two-dimensional? Well, turns out that there are these special trees, data structures called spatial trees, and they basically represent spatial data. And so each time you go in, you're going one level in the spatial tree. So this is some pretty cool stuff. And I know this because in my CS61B course, our last project was to implement a cheap version of Google Maps for the city of Berkeley. And this was an amazing project because we had to build our own cod tree, we had to use it to get the right images and basically render that onto the screen. And it was really cool. But what this really wouldn't have been, there wouldn't have been an efficient way to do this unless we had trees. Trees were the most efficient way to do this, and people who didn't use a tree had a hard time with this type of problem, and even if they got it to work, it was extremely slow. So this is again why trees are very important. They're very efficient for getting information that's in this type of structure. Okay, so this was the last content-based lecture of this course. In the next video, I'm going to go over a lot of practice problems on the stuff we've been talking about for these past few videos, because there are some pretty tough topics. I will go into some harder linked list problems, some harder tree problems, how to approach these type of problems. And so yeah, that's something to look forward to. And also in the last video, I'm going to give basically a broad overview of what we've actually achieved in this video. So it's going to be a huge summary, and it's going to be really cool. Anyway, thanks for watching. I'll see you next time. Thanks.